Hello everybody, this is Marco Chan from South Survey. I'm in Guangzhou. Today, I will give you a total presentation for our brand new total station. The Navy station. I record a short VCR on a construction site in order to show you Navy station performance better. Let's watch first. Hello everybody, this is Marco Chan from South Survey, the engineering product manager from International Business Division. Today, I will give you a presentation about our brand new total station, the Navy station, which integrate the Intelligent Operating System, GNSS technology, and with dual laser EDM as one. Navy station delivery fast and reliable positioning using all available satellites with 496 channels to produce a high precision solution. Benefit from the minimum size and lightweight. Our own developed GNSS board can be complete match the requirement of total station and meet the demands of your specific jobs. It also comes with a variety of the data communication options. One is the UHF radio mode. One is the external network mode. As we can see in the screen, we can choose the UHF mode here and go to the network mode here. About the mechanical structure, Navy station features world's first dual laser EDM with the 2000 meter refractory range, combined with a stable intense ball axis. You can be confident that it can be achieved the high level of 1 second accuracy with every measurement. About the technical introduction, I will show you later for the details. Next, let's talk something about software, which is also the most important part. Navy station have the abundant onboard software that is easy to use and flexible based on the unique Android platform. Expect the powerful data collecting software, and the mapping software, and a special package of the road, bridge, and tunnel on board. You can select or develop your own software on Android platform. We have a connection platform called TS Server to help you connect the linkage between the hardware to your own software. The specification and commands can be read through TS Server. As you can see, I'm on a construction site right now. Today, I will using the Navy station to do a simple measurement. I will set up the occupy point in the random place to make a measurement and show you how it convert the virtual coordinate system to the real coordinate system we need. So the first, we go to the setup station point. In the station point setup, we go to got the GNSS data. Here is the random place I choose. So the first, we can see the details for the satellite. We get the satellite details here, and we got the fixed coordinate here. And then I press O to save the point. And for the backside point, I can using any angle I want. But this backside I need to aim the next backside I will using later. So I set. So now the field station is a setup finish. I can start to measurement. So I just measure around 10 points here. So for the Navy station, we also have the other function for the graphic. So this we can load the map. So here we can see I measure the point is here, but this is not the real coordinate because I just set up the backside in the random angle. I just want to show you now the map shows like this one, and then I will move the station to the backside point, and then I will using the reduction function. At that time, we can get the real coordinate we need. So we can check this map a little bit later to compare what is the difference. So After I make the side shot in the station 1, I will move the station to the station 2. That is I set up the angle in previous station 1 in random angle. But when I go to there, I can get the real angle and real coordinate system between these 2 points. And at that time, I can reduction all the side shot from the station 1 and convert to the real coordinate system. So now I set up the station on the previous backside point I random choose. I got the GNSS data, and this is the null point, and the station 1 became the null point. So I set the station as the null point, and I using the Google function for reduction to change the first station or the side shot point in that station points in the virtual coordinate system, and using the reduction choose the correct backside, and he will recalculate and will show us after the reduction the real coordinate system. We can see on the map here what is the difference compared to the before. Today the outdoor simple measurement demonstration is done. I will present the other details technology from the Navy station in indoor. I see you later. So welcome back to indoor. So let's take a quick look for the key features and the specs. Even I make some introduction in the VCR. So for the Navy station, we have the world's first dual laser technology EDM, Android operating system, high resolution TFT screen, expandability SDK, abundant data exchange method, visualization graphic data import. For the key specification, it supports all constellations, including the GPS, Galileo, GLONASS, BDS, and it contains 496 channels. For the internal UHF radio, the power is 0.4 watt and working range 8 kilometers. And for the cross network, the data link, the range is 13 kilometers. And for the EDM part, with the 2,000 meter refractory range and 1+1 ppm 1 second accuracy. So I will start from the software, not like in past I make the presentation, I always present the hardware platform first. But for the Navy station, I want to show the software part first. And from the VCR, I already show you the main function for the Navy station. So in here, in the office, I would like to introduce some other functions on the software. So on Navy station, we have the 2 default programs and 2 optional programs. The first program is the TS server. This is a service program. Connect the hardware platform and the software. It can distribute the measurement result to the different programs. For the survey star, it is a basic data collect program in the field, and the mapping star is a drawing program when you survey in the field, and it supports the point, night, plane, and have many tools to help you drawing the map when doing data collect. The RPT star, it is a special program focused on the road, bridge, and the tunnel project. So we start the survey star first. From this picture, we can see it is like the function just like the similar normal TS function, but when we have the GNSS board integrate as one, it should be something different. I would like to talk about the reduction function. This is one of the most useful functions for the Navy station. When I have a Navy station, I can set up the free station as an occupied point anywhere and set up the backside as I want. I do the same way in the VCR. And for our experience, normally when we're using the total station set up the control network in the surveying field, the first point is to lead the occupied point to the survey area. Sometimes the occupied point or the node point location is far away to the survey area. So when we have the navigation station, we no need to spend more time to lead the points from the occupied point to the survey area. So when we have the reduction function, also things is I can set up the backside anywhere, and then I use the reduction function to change the coordinate system to the real one I want. So for this picture, actually is I measure the points on the construction side. In the left picture, we can see is the before reduction. Because I set up the backside as the angle I want, I input is the 15.5 degrees. But we can see on this map, actually it is wrong. We know because they have the background map show us the coordinate shows here is not correct. And this is before the reduction, we connect we measure the coordinate by the total station. And the first line, this coordinate is we get it from the GNSS receiving board, and then I choose it as a station 3 station. And when I move the station to the backside point on the station 2, at that time, I use the GNSS receiving board. I can get the real coordinate on the station 2. So in here, I'm using the reduction function to change all the side shot I do on the station 1. Totally, I measure 20 points, but here I just list 8 points to show. So we can see here the coordinate. For example, in the point 3, the large 3 digit is the 351, and here is the 543, and also the E coordinate, the east coordinate. So after reduction, we can see on this map, okay, actually this is the construction site area. And for the other friendly function is the automatic update. It can automatically update online when we release a new firmware version. So when we release a new firmware version, it can be detected by itself and ask we need to upgrade or not. So from the first picture, we can see the old version I'm using is the 19 October 29. And then when in the 2020, I test the instrument again, he will remind me there's a new version found and want to update or not. I just keep the update now, and he will download and automatically update. Finally, we can get the update version. So this function is to keep our users always can use the latest version we release. And for the other option program is the mapping star. Mapping star is for the optional onboard program. It offers a special drawing tools to help you measure and drawing map in the field. It has the 4 models. One is the station, one is the job, map, and set. As we're using the total station in past, actually data collect in the field just the first step we do. We need to make the project done. After the data collect in the field, we need to download the data and proceeding the data in the PC software. Normally, it's drawing a map. So here we can see, I'm using the map star to measure the same points on the same construction site, but this is quite different compared to the survey star. From this picture, we can see here is the wall I measure, and this I measure a couple small, the simple building here. When I enlarge, it will give you the property by the program. And when I export the data, I can export the coordinate data and the raw data and also the graphic data. When I export this, the drawing file, and open by the CAD file, CAD software on the PC side, we can get this one. So it saves our time to drawing the map in the office. For the other package, have the road, bridge, and tunnel star. This program now, we are under develop the English version. So here I only have the Chinese picture to show you. For the road, it allows you design and state out the road data on the construction side. And for the tunnel, it also, you can define the alignment for the horizontal and the vertical. Also, he can calculate the exaction, the state out point, and the overdue or the short of the due on the date, and so on the data. And for the data format, for the coordinate data, we have the DAT, DXF, TXT, and CSV. For the raw data, we have the TXT format. And for the graphic data, we have the CAS and the GBKG. And the TS server is the distribution platform. The function is for this program is allow the application to read the hardware inform or input the setting value here. As we can see on the left picture, all the setting, whatever we running on the survey star, mapping star, or the RTP program, all the individual program, the setting actually is connect to here, to this basic server settings. And on the right side, this is a raw data output, the screenshot. And based on this server service, it allows navigation running multitask in the different program. We offer SDK for third party to develop your own onboard software, such as special for shipbuilding, large workshop facility installation, oil tank project, and so on. So we can see here, this line is the hex type command. This is we including in the SDK pack. So the developer, they can using this one to develop their own software. This is we want to enlarge our customer group for the Android platform. So up to here, I finished the software part explanation, and we will go into the hardware part. So for the navigation, we have the new EDM technology. So the first is we think about is what are the advantages of this new EDM. So let's see a few short video first to get some image about this new EDM technology. The first, outdoor 200 meter. So when we measure around the 200 meter, we can see the data jump only 1 millimeter. And the speed is quite fast. And the target on this is the building sidewall. And when we enlarge the measurement distance to around 400 meters, you can see the slope distance. 261, 265, 263. So the maximum data jump only under 5 millimeters. Okay, let's go further and we change the target. And this time I aim on an electronic tower. The range is the 550 meters. This is the target I aim on, the yellow one. So using it, I press the measure key. And we can see 030, 3023, 032. So, and then we go further. We go to 1,663 meters. 233. So through this couple shot the distance measurement outdoor, we can see the most advantage for this dual laser EDM is about the accurate, stable, and faster. And as we know, when we work in the field, mostly the non-piston range is under 500 meters. So when we can see in the short video, 200 meter, 400 meter, the data jump is quite stable. So actually, this is the most benefit bring to our users. And not only about this one, we can see the other data form to compare the old type we have. The first form is our new EDM, the data tag. On 500 meter, the data jump less than 6 millimeter. Just so in around 200 meter, it only 1 millimeter data jump, and 400 meter is a 5 millimeter. So around 800 meter, it less than 10 millimeter. Not only on the refractories, the accurate is increased. Even in the prism range, the offset, even offset of the prism center around 3 minutes, it still can less than 1 millimeter accuracy. But compared to our old type, 400 meter, is around 25 millimeter data jump. So this is the most benefit and the direct feeling can bring to the users. The new EDM technology increase a lot. So for this dual laser EDM, we need to ask is how we make this come true and what technology make it outstanding. And in the normal EDM, there are 3 models. One is the light reducing model, one is the in-out path model, one is a mode model. In here, I would like to tell you some about the motor's function and the total station working theory. For the light reducing model, he is a filter model. He works with the filter, and his main function is when we using in the prism mode, because the prism refracted signal is quite strong. So, but when we measure the target, the distance from the couple meter to 100 meters, the return signal, if too close, is too strong. If the target is too far, so the return signal is weak. So we need the light reducing model to control all the return signals should be in a certain range so that our EDM CPU can process the signal. And for the in-out path model, the function is for when the laser beam goes outside, all the return signal, not only including the laser return signal, including other noise, the car sounds, the car noise, and the sunlight, and the other influence signal will come back through the EDM lens. So the in-out path model is when we send out a laser beam, that's we call out path. But we need to keep one in-path laser signal to compare the return signal, which one is the correct in the certain range we need it, so that our CPU can proceeding the electronic signal. And for the mode model is the control from switch from the prism mode to the non-prism mode. So basically, is the in-out path model is make sure the EDM accuracy. So the question is this model is so important. So why we use the dual laser technology to control the model instead of the mechanical paths? How to keep the distance accuracy? So in here we can see this picture is the new laser diode, and the bottom one is the old laser diode. And we can see we have the two laser diode for emitting laser also, for emitting laser. And how it works, this one. Because the first we develop our own develop the laser drive circuit we call SA11. So it will control by this circuit SA11. When we need the out path, we're using the out path laser diode. And when we need the in path, we're using the path laser diode. This is controlled by the circuit SA11. And the advantage for this switch by the electronic control is the switch time of the circuit control is more faster than the motor switch time. But there are another issue will comes out when we're using the two laser diode, because it's the frequency drift by the temperature difference cause the distance drift. Let me explain here, because the laser diode is when we're emitting the laser, we have the certain frequency. The frequency is generated by the crystal oscillator. So when we're using this one, when we're using two laser diode, it means have the two laser frequency. We need to make sure this two laser frequency in the really accurate range, so it won't cause the frequency drift to cause finally the result is different. So in order to solve this problem, we improvement our electronic circuit. The first, because we're using the circuit control, so the laser goes out and the return signal is speed up. It means that more and more signal we need to proceeding. So the EDM processor, we upgrade from the Cortex M3 to the M4, and at the same time, we reduce the power consumption and increase the proceeding speed. And for the distance and the speed and the relationship is not about the times, it's about a square. For example, I measure 10 meters, the noise signal is 10. But when I measure 100 meters, it means the distance just increased 10 times, but the signal come back, it will increase 100 times. It's a square relationship. So here, we need to reduce the interference because the noise of the signal increases a lot. So we need to reduce interference of the line with the less straight line. The value of the return signal will be closer to the actual value. That's why the measurement is accuracy. And also, because the electronic tape is shorter, because the frequency we increase up to the 115 megahertz. So at the same time, we also need to upgrade our internal electronic clock, the SC80 clock circuit chip with the shorter tape. So the speed of the time calculation is increased twice as fast as before. And actually, the other thing is the optimize the whole circuit design with the less interface. Under non-pixel mode, the SA2 transmitter amplifier is able to cancel the interference signal on the same frequency to the circuit. The SA2 is our totally developed by ourselves. So this SA2 is the key part for the electronic circuit we develop or we solve the electronic issues. But when we improve the electronic, that's not enough for the total station EDM, because we know for the total station we call it is the mechanical, optical, electronic, three parts combined as one. So the thing is for these three parts, they interactive to each other. The optical correct not means the electronic is okay, but we need to make the three parts, the mechanical, electronic, and the optical work together well and achieve our requirement for the accuracy. So here we can see we changed our optical path. The first, we can see on the top, this is our uptight EDM. So the number A is the emitting laser diode, and he will go to the tail of the mirror, and reflection first time go to the center of the telescope, and the laser dot goes out to aim our target. But for the new EDM, we change the position for the laser diode to the 7. So we can see here has a two laser diode. One is for the out path. When we need to aim and measure the target outside, the out path laser diode send only one reflection and goes out. And controlled by the SA11 circuit, it will switch to the 7 here to send the in-path laser go to the receiving fiber directory. And for the optical things, the most difficult thing is the optical signal is invisible. But all the optical signal is affect the distance accuracy. And all the light return signal will transfer to the electronic signal, then we process the electronic signal. For the lens, objective lens on here we call some prisms in the internal optical path. We all know the material is the glass. When we design or optimize for the optical system, we need to consider a lot of the parameters, such as the coating, sealing, anti-shock, keening level, light transmittance, because they are our eyes to see the target. Also, they are the EDM eyes to aim the target. For the EDM technology, the biggest issue is that we need to handle the optical signal and the electronic signal relationship. For the optical part, try to filter more influencer signal. For the electronic process, after enlarge all the signal we got, and then we process the correct signal. Maybe this drawing is hard to understand, so I make the objective lens pictures. So here, we can see here, this is the R6 objective lens, and this is our new EDM we call R15. And for we make the very big change. The first, we cancel this tubing. And for the new EDM lens, we drill a hole in the center. Make the laser goes out didn't affect by the tubing when we using before. This is for set of the screw stacks. In the R6 EDM, we fix the objective screw by two fixed screws and one passing ring. Now we drill a hole. The laser can goes out directly, no relay to the objective lens position. Therefore, to increase the stability. Drilling a hole on the lens is a complicated technology. It is easy to damage the lens during drilling. We test many times and finally we got a solution. So for the lens and the laser diode position change, and we can see this can be viewing by the users. On the top is our laser dot size. On the bottom is the Leica laser dot size. So on the first picture, the distance is the 10 meter, and this is the R6 laser dot. The diameter for the laser dot is a 5 millimeter. For the new EDM is a 3 millimeter, and for the second pictures, the distance is 35 meters and diameter 16 millimeter. And for the new EDM, 12 millimeter. It means even the farther distance, the laser dot size gets smaller than before. And here is the 15 meters. 22 meters for the R6 EDM and 16 millimeter for the new EDM. So we can see this is the mechanical part structure for the R6 EDM. The first here is the laser diode emitting, goes out, and this is a refraction prism. First time refraction to the center, the probe prism, and second time refraction goes out. In past, we fix this lens by 2 screws and the press ring. So when we adjust the emitting laser axis, we need to loosen the 2 fixed screws first. At that time, the lens is in loosen status. So after we adjust the emitting axis, but the screw will have the stretch release, so will affect the accuracy for the axis. And for the new part, for the new EDM, we change the mechanical part. Here is the emitting lasers for outdoor. So we add a mirror in the central, and he can focus the laser dot. Only one time refraction. And here we drill the hole. So the axis goes out, not relate to the lens anymore. So in this time, we can increase the stability for the emitting lasers. Actually, for this, the design diagram is not easy for understand. So I prepare 2 types. The EDM here, I will show you in here to give you an explanation and let you more easy to understand. 有个实验2，是不是这边啊？不是。你可以过来拍这里，你先拍这里就好，你先拍这里就好。So this type is our old type, the R6 EDM. So we can see here, this is the laser diode on the bottom side. So when he go out the laser, this is the motor. 你可以拍得到吗？你可以拍得到吗？ This is the refractor prism. The laser goes out and go to center and comes out. And this one is the new type EDM. We totally change. We can see here have the dual laser. This one is the out path laser, go into the center and comes out. And this one is the receiving fiber. Here on the bottom is the in path emitting laser. He will directly send the laser signal, go for the receiving fiber here. So we can do a simple test here to compare the difference. This is an old type EDM. So now we go to the simple measurement, the distance. So continue mode. So we measure. We can hear the sound. Click it, click it, click it. 你可以看到这个吗？可以拍到这个激光点吗？可以拍到这个激光点吗？ So we can see the laser dot here is a fraction, and the sound is a click. Every time it go to the in path, out path to get the correct result. And for our new EDM, for our new EDM, we can feel the sound is more speedy than the mechanical part control. Because for the old type, it is they has a limitation by the motor switch time. OK， 可以了，这里你就切回来吧。And for the technical explanation and for the total station, actually is not only work in the R&D department. For the total station, actually it is very important for the production control. In the next, I will show you a video from the factory side to see how we produce the production the total station, and I will give you the explanation. So the first, this is the bearing ball vertical axis. Now we're using the bearing ball axis for the vertical axis and the horizontal axis. The first, when we got the raw material, we need to clean it first by the supersonic cleaning wave. This is for the cleaning. But not only the machine cleaning, just the first time. The second, we need to hand cleaning to make sure each part match our requirement. So put some oils for the excess, and here is for the absolute disc in it. And then we're using the micro telescope to check the encoder disc, each one, and the test meter to check the roundness. This is make sure the axis, the roundness, and check the CCD signal here. After the components pass our quality check, and we will go to the assembly line. The first, we will assemble the vertical axis. And this is the tangent screw production. The tangent screw actually is quite important for the accuracy or for the stable things, because the screw distance is required in the 0.35 millimeter. And for the 1 second accuracy, we're using the 0.25 millimeter screw distance screw. And this one we need to hand assembly by the workers, because for the tangent screw, you need to make sure the turning feeling is good and smooth. And now for the EDM housing, the telescope tube in it. Before the lens goes for the assembly, we need to clean both sides, inside and the outside, for the objective lens. This is a pull-off prism for the eyepiece using. And this part is for the check the compensator accuracy to set the constant for the compensator. And this is the horizontal tangent screw. Go straight horizontal axis. So after tie the screw, we need to put the group on it, make sure the screw slacks and the bearing for the horizontal axis. And after that, we need to rotate the EDM housing to make sure it goes smooth in any angle. And then assemble the vertical tangent screw. Dip the group on the screws. For the CCD, the fault detector on the CCD, encoder disc. This is a dust cover for protection. This is the prism in the center of the EDM. So we install the objective lens now. So push in and tie the screw. And take off the special tools. This is the patch ring I mentioned before. And compensator installation. So in the first time, we need to check the optical specification, the parameter. We check the 2C, eye angle, index angle. So the first in here, we need to make sure the optical specification. And then we go to the installation, the EDM electronic part. The first, install the sliding ring now, so it can get the power supply from the mainboard, go to the EDM part. And install the angle mainboard, and connect the CCD wire. Display unit. And then we start to install the mechanical motherboard for the EDM side. It connects the optical coupling here and the emitting laser diode. After that, we need to check the emitting axis, same as the telescope axis first. We set up the target around 30 meters away from in the building and using the mirror, so the double run is around 60 meters. When he send out the laser diode, he will come back to this center. The crosshair will aim the center directly, and the laser diode should be at the same exact position as the crosshair aim on. So this need to adjust a little bit. So he will adjust. This is our special tools to offer the power supply to the emitting lasers, because now it's not finished for the EDM board installation. So after the laser diode emitting adjustment, we need to double check the specification for the collimation, index angle, and the high-low level. So now she's using the pin to adjust the vertical. So after the emitting, we need to go to the adjust the receiving fiber here. We're using a theodolite telescope. Aim on it and adjust the receiving fiber. The laser dot should be same as now. Okay. We put the fiber on it, the receiving fiber, to adjust the position. It should be same as the reticle center. All the screw is tight, and double check. So this go through the housing. For the next installation, the EDM board. Dip the group on each screw to make sure the screw tracks is not affect the accuracy. So now install the EDM board and connect all the wire on it. And now we need to check the in-path reading, the in-path, the value reading. This is the baseline. We check the laser diode, the tolerance, for the pace tolerance. And this, it can automate to move by the control. And the accuracy is a 0.1 millimeter. Each unit, we need to come here to measure and record the tolerance for that unit. And this is the aging room. All the instruments, after we finish the installation, we need to go to the aging room, stay for 48 hours to make sure all the checks goes out. And after aging, we go to the QC department to do the final check, the final inspection, make sure all the specifications match our design requirement. This is check the tube, the compensator, dip the groove. So this is a QC department. We're using the roundness checking inspection to check the angles. And each unit have the ID, the records. This arrow is the record for the whole process during production. So to here, the factory tour is finished. So today, thank you for your time, and